Alright, welcome. Today we want to look at thermodynamics. So we want to have introduction on thermodynamics, which is tagged MEE 206. So to start with, what is thermodynamics? Thermodynamics is the science that deals with the interaction between energy. It deals with the interaction between energy, heat, work, and material system. Is that taken? So thermodynamics is a science that deals with the interaction between heat, energy, work, and material system. There is no way we can explain thermodynamics without laying emphasis on these four things that I listed out. Alright, so we now have some terminologies that we normally explain in thermodynamics. Number one of it is system. What is a system? In thermodynamics, a thermodynamic system is a prescribed region in space containing a collection of matter. So a thermodynamic system is a prescribed region in space containing a collection of matter within an identifiable boundary. Look at this diagram. Let's consider this diagram. Is that taken? So this is a system. For example, you have your gas cooker or anything you are using to cook. Then you now have your pot. You want to heat water inside the water. Inside the pot, it has cover. Assume that it has cover. Use the cover. You understand? So inside this place now, we now have water. You understand now? So the whole of this thing, it is regarded as what? Thermodynamic system. It is a system. So a system is what you study in thermodynamics. You understand? So the identifiable boundary are this line. Is that again? That covers what you have in the system. Is that again? Everything that covers what you have in the system, it is regarded as boundary, or they call it surrounding. Boundary or surrounding. Hope that is clear. So the whole of everything is regarded as what's it called? System. Is that taken? So now another thing that we must distinguish is control volume. Is that taken? And before I move on, so anything outside the system, it is regarded as the environment. Is that taken? It is regarded as the environment or the surrounding. So this one is the boundary. Not this one. This place like this is the boundary. So anything outside the system, it's regarded as surrounding. Okay, let me consider another thermodynamic system. Okay, in this case, then I have something like this to make it more clear. So this is the thermodynamic system. Is that taken? So it is a region in space that consists or contain a collection of matter or mass within an identifiable boundary. This is now the identifiable boundary. Is that taken? But here, anything outside this boundary, it is regarded as the surroundings or the environment. So from here, these are the what? The surroundings or the environment. Is that taken? So what we are studying, it is regarded as the system. Now, another thing we must understand clearly is what we call control volume. Control volume. Is that taken? So a control system is almost the same thing with an ordinary system, just that what distinguishes control system or control volume from the system is that from ordinary system is that control volume is used in the case of an open system. So for a control volume, it allows matter to comes in. So when you have something like this, can draw any shape, nobody will penalize you for that. So matter is coming in, matter or mass is coming in, and at the end here it goes out. Is that okay? So when matter comes in and goes out, that's when we have what? A control system. Now in this case, now let me use another pen, red. Okay. So this is now the what? The control volume. This is the control volume. This is the control volume. Now let us now consider types of system. Types of system. Types of systems. Number one, we have a closed system. In this case, when we say that what a system is closed, is that taken? When a system is what is closed, number one, there is a fixed mass. Fixed mass is involved. A closed system is a system that consists of a fixed mass of matter, meaning there is no what? There is no mass transfer. Mass is not coming in nor going out. You understand? If you put your pot on electric stove or whatever, you want to boil it, you already have a fixed amount of water inside the pot. Is that taken? Now you are now applying heat. The heat that you are applying will make the water to change states. You understand? But in this case, I'm only referring to what? To a closed system now. So the system is what is covered. As a result of you covering the what? The pot, then the heat that you are applying, is that the thing will start what? Boiling. You understand? Then it will definitely change states. You understand? So in this case now, you are applying heat. Is that again? Due to the change of state, water now changes to what? It changes from liquid to steam, meaning that work has been done. So in this case, a closed system consists of a fixed mass. Is that again? It simply means that there is no transfer of mass, but work and heat can move across the boundary. Work, which we will term W, and heat, which you call Q, can move across the boundary. So can move across the boundary. That's what the case of a closed system. Diagram. Let us represent that in a diagram. We have to represent it in a diagram. So here, because for everything you are doing, especially in exam, so it is expected of you to represent it in what? In a diagram after you've defined that particular thing. Okay, so this is the system itself. Is that okay? This is the system. So let me use this guy. Okay, thank you. So yeah, all these places that I'm covering now, they are the surroundings. These are the surroundings. I hope that is clear. These are surroundings. Okay, so that's not important for now anyway. Let me uncheck this. Okay, so here there is a fixed mass. This is a system. Is that again? So fixed mass is there. Then it has, this is the boundary. By definition, this is the boundary. The boundary distinguishes the system from the surroundings. So that's just the layer that you have. So another thing is work. Heat enters, Q, which is heat. Then work comes out, work. Is that taken? There is no, for a closed system, there is no mass transfer, but work and heat can move from across the boundary. They can move across the boundary. So another types is now what we have, what we call open system. What do we call an open system? What is an open system? An open system is a system that allows mass transfer. It allows mass transfer. Let me use this. Beautiful. So here mass enters. Is that taken? It enters here and comes out here. It enters and comes out. You understand? So it is in an open system that you have. That's where you have control volume. It is an open system that has a control volume. So this is the control volume here. You understand? So mass comes out and this. So this one allows both mass can be transferred, mass, energy, and work. Is that taken? So the heat which is Q, it comes in, then work goes out, W, you understand, and mass. So now the third one that we have is known as an isolated system. An isolated system. What is an isolated system? So this system has a fixed quantity of mass, like closed system. A closed system also has a fixed quantity of mass. It does not allow mass transfer. Is that taken? But what happens to this isolated system is that there is no mass transfer, there is no heat transfer, and work is not being transferred. You understand? So it is an isolated system. So when we say that an isolated system, it simply means that our W and Q, they are equals to 0. So it does not have any interaction with the surroundings. An isolated system does not have interaction with the surrounding. So by drawing, just trying to distinguish so that we can see it clearly. So understand? So this is the boundary. This is the system itself. This is the boundary. Is that taken? So in this case now, there is no heat nor work. So here we can say that no mass transfer. And another thing is no mass transfer across the boundary. So it does not have no heat across boundary. No heat across boundary, and no work. No heat across boundary. So they can ask you in exam to distinguish the three, or anyhow, or what can you say about isolated system, a closed system, and an open system. So in some cases we also have this system that we call homogeneous system. Homogeneous system simply means that when the fluid are in the same phase. Is that again homogeneous? So a system which consists of a single phase is termed homogeneous. And we have another one which we call heterogeneous. So heterogeneous system is a system which consists two or more phases. A system that consists two or more phases. So that's what we regard as an heterogeneous system. Okay, let us now go to another important thing. We have properties of a system. What are the properties of a system? Properties of a system. We are going to discuss property, states, parts, processes, and cycle. So to start with properties of a system. So the characteristics of a system is the physical property, which will take it as the physical condition of that system. Is that the characteristics of every system is its physical property, which we know to be the properties of the system. So a property depends on state of the system and not how the state is reached. Let us assume that, where is my pen? Okay. Let's take for example that we want to move from here to here, from point 1 to point 2. This is point 1, this is point 2. You understand now? So a property or properties, they depend on how, they depend on the states of the system. The states, this is state 1, this is state 2. For this state 1, is that if you have to consider this state 1, we don't care on how this system is what is reached. Whether you move like this, if you have this one like this, I can also move from here to here, then I've gotten to point 2. You understand? Whether you move like this or you move like this, you come here, we are less concerned about that. Is that the only thing we are concerned of is what? The state of that system. You understand? So we don't consider what the pathway. That's just it. So example of these properties, we now have example, common among the example, we have pressure, which is P, volume, we have volume, we have temperature, we have mass, we have entropy and the likes of them. You understand? So as we move advancedly, so we'll be getting used to all these properties. So characteristics of a property has what characteristics? Number one of these characteristics is that you must know that properties does not depend on the process. If you want to move from here to here, is a process. Exactly. You are coming here, this point 2 is the same thing of you coming, you move from here to here, then goes up. Is that again? Any pathway you follow, we are less concerned. Is that again? So property does not depend on the process. This is process 1. You just take one process. But if you are moving from here like this, you want 1, 2, you consider 2 processes. You understand now? So we are less concerned about what? The process. The only thing we are concerned of is what? Is the end point, as in the states of that particular property. So here now, so property does not depend on the process. And secondly, so property depends only on the states, on the end states. And thirdly, so its differential is exact. Its differential is what? Is exact. Its differential is exact. So another this thing, we now have what? We have types of properties. Like in our basic physics, we were taught units, as in dimension analysis under it. So that way we have what units? We have fundamental unit and derived what unit, and fundamental property and derived what properties. So here also we have what fundamental properties. So for our fundamental, there are 2 types of properties. We have fundamental properties. When we say fundamental, that's the basics. Is that again? So which other one depends on? So the fundamental properties that we have, they are just 5. We have 5 fundamental. Please take note. They are 5 in number. We have pressure, temperature, we have pressure. Number 2, we have temperature. Number 3, we have volume. Number 4, we have entropy. Then fifth one, we have internal energy. So pressure is capital letter P, volume is capital letter V. So pressure is capital letter P, capital letter T, volume. Entropy is S, and internal energy is capital letter U. Is that because as time goes on, you'll be seeing small letters. So anywhere you see small letter, we are referring to specific. Then it is specific volume, specific pressure, and specific internal energy. You understand? Now the second one is now the second type. Let me call this one A, and this one is B. So the second type of property is what we call derived properties. For a derived properties, we have number one. Among them, we have Helmholtz free energy, which we use capital letter F to denote, and the formula is internal energy minus temperature multiplied by entropy. So this is Helmholtz energy. Now the next one is Gibbs free energy. Also Gibbs free energy, we use capital letter G to denote that. So the formula is H minus Ts. This one is the heat. Now the third one, this is enthalpy. So the third one is enthalpy itself. Enthalpy. ENTALPY. Enthalpy, capital letter H. Is that taken? So we have U plus work, PV from Boyle's law. In your gas law, you have PV is equals to K, constant. Is that taken? So the unit of these two gives what? Joules. So you can call it work. Is that taken? So this is what? The work. So your enthalpy is equals to H is equals to U plus PV. Now, another thing is now what? Classes of thermodynamics properties. Now, all these properties that we've considered, they belongs to particular classes. You understand now? Let me add page. So classes of thermodynamics properties. We want to look at classes of thermodynamics properties. What are the classes of thermodynamics properties? There are three classes. We have intensive properties, we have extensive properties, and we have specific property. To start with, let me begin with intensive property. What are intensive properties? Intensive properties, they are point functions and are independent of mass. Point function and they are what's independent of mass. Example of this, just know intensive properties are point function. Exactly, meaning that if you have your graph, you can easily locate them on the graph. Whether you have PV graph or TS diagram, you have PV diagram, pressure volume diagram, or you have TS diagram, that's temperature and entropy diagram. You understand now? So you can easily locate them on the graph. You understand? So here, let me erase this. So intensive properties are independent on mass. Let us take for example, if you have, this is a bowl, you have water inside this bowl. So this water is let me put 90 degrees Celsius. Is that again? Now you now have smaller cup. You understand now? You take part of this water, Let us assume that this water is 50, no, no, 5 kilogram. You understand now? 5 kilogram of this water. Now you now take just 2 kilogram out of this water, or let me say you take 1 kilogram out of this same water, which is 90 degrees Celsius. Is that taken? You want to prepare tea. You have the water inside your jug. You understand now? Your kettle. Let me say kettle. Now you now take part of the water. You put it inside your cup. They are still in the same. They are the same temperature. Is that taken? Nothing happens to the temperature. Meaning that, look at the mass. The initial mass from the kettle is 5 kilogram. So for the cup is now what? Is now 1 kilogram. So temperature is independent of mass. You understand now? So temperature is an intensive property. Temperature, T, is an intensive property. Now this same water, you understand now, what is the density of water? Density of water is 1000 kilogram per meter cube, 1000 kilogram per meter cube, or 1 gram per centimeter cube. You understand? Nothing changes to density with respect to the boiling or whatsoever. Is that taken? Density is an intensive property. Is that taken? So kinematic viscosity is also an intensive property. You understand? So you also have pressure to be an intensive property. I hope my explanation is clear. So an intensive properties, they are they are point function. That's one. And they are independent of mass. So the second one we have is now extensive properties. What's an extensive property? An extensive property are those properties which are dependent on the mass of the system. They are dependent on what? On the mass of the system. So anything that you have that depends on what? On the mass of the system, it is regarded as what? As the extensive property. Okay, another example. Okay, let us assume that we have water of different temperature. Okay, no, water of the same temperature, of the same enthalpy. Let me use enthalpy H. So 1 kilogram of water with this enthalpy H. Is that taken? Then you have another similar water. Is that taken? Of 1 what? Of water of H. So these two water are in different bowl. This one is here and the other one is here. You understand now? So you now pour the two in the same vessel now. Is that taken? So as you are pouring the two in the same vessel, your H, this one has H, this one too has H, then this one becomes what? 2H. Is that taken? So enthalpy is an extensive property. You understand now? Enthalpy is an extensive property. Enthalpy is an extensive property. Among the properties that are extensive in nature are volume, enthalpy, entropy, and mass itself. Volume, enthalpy, entropy, mass. A lot of them like that. So if you want to convert what's it called, extensive property to intensive property. So if the volume of a system of mass m is V, then the specific volume of matter within the system is this. So there's now something that we call specific volume. So if the volume of a system is V and its mass is what? Is m. So the specific volume is now what? The actual volume divided by what? By mass, then which will give us what? Small letter v. This is what we call what? Specific volume. This is a specific volume. Is that taken? So we now have what? Specific properties, meaning that any properties divided by temperature. Now we have specific entropy, what's it called, specific enthalpy. Normally enthalpy is capital letter H. So if you now have specific enthalpy, that's enthalpy divided by mass, then this one give us small letter h. Just know that the small letter of the one you are dividing by mass is what we call specific. This is specific volume, small letter v, specific volume. This is specific enthalpy, specific enthalpy, h, enthalpy. Is that taken? So we have internal energy. Is that taken? So normally our internal energy is capital letter U. So if you are not dividing it by mass, becomes what, small letter U. So that's specific in nature. Is that taken? So that's what you should know in that regard. So another thing we need to explain, quick one, is what we call thermodynamic cycle. Let's assume that so we have this point, we have this point here, you understand? So here moves like this, move like this, come here. So this one goes like this. Let me use another arrow. This one goes like this. This one also goes like this. I already explained what a process is. 1, 2. This is point 1. This is point 2. When you are now moving, that's a process. This is a process now. Is that taken? So in this case now, you can move from here to here and get to 1. Gets to point 2. You can also follow this route, and also you can also follow this route. This is process 1, process 1, process 2, and this is the third process, process 3. Is that taken? So what is now a cycle? A cycle is a cycle is a process or series of processes. This is a process or series of of processes whose end point is equals to the starting point. So you move like this, you go, then you come here, then here. You understand? So that's what for the so this is a process. This is a diagram of process. I would have said this is a diagram of process, but for a cycle, so you start from here, point 1, then you move all around. A cycle is what? Is a series of processes, or a process where you will have your starting point is also your end point. So you move like this, you go around, is that you still come back to the same point. Then that is what we call a cycle. That is a cycle. Is that again your final your starting point is is your end point, or your initial state is your final state. So another thing that we have, we now have we have part and point function and part function. For point function and part function. So for a point function, is that again its integral is exact. Its integral is is exact. So we have let's assume that we have v2 here and v1, then dv. If you integrate this one now, the integration of dv will give you v. Then you had your limit v2 v1. So when you have v2 minus v1, and if it is in terms of pressure, That's P1, then P2, sorry, P2 here, then P1 here. Then you have dp. So if you do that also, you are going to get P2 minus what? Minus P1. So a point function is any thermodynamics property that could be combined to locate a point on the graph. So you know we have what? PV diagram and we have TS diagram. So you can use pressure to locate a point. You can as well use what? Volume to locate what? A point. Is that okay? So all these are what? They are point function. For T also, we can use temperature, we can use enthalpy, entropy. They are all what? Point function. Is that okay? So these are what? These are point function. Just one thing you need to know is what? It's differential. Is that okay? It is exact. Look at it now. dp, it give you what? Exact. Now we now have what? Part function. Part function are function that cannot be located on the graph, but they are the what? They are the area under the graph. You understand? So example of those ones are work done, work, and eat. You understand? So in this case now, the differential is not exact. The differential of what? Of part function is not exact. So you have this. For a part function, you have 2, 1, q. So this is not what? This is inexact. Inexact. So if it is in terms of work, it is also the w. So that's the point function and part function. If you are asked to distinguish between what? A point function. A point function, they are the what? They are the properties that can be used or that can be located on the graph. That's one. But a part function cannot be located on the graph. Another reason is what? Another point is that point function, their differential is exact, but for a part function, their differential is what? Is inexact. So here you can now have this one finally to be q1 to 2. Is that taken for it? So for work, it will be w1 to 2 for work. That's just it now. So we've explained process, functions, part functions, and point function. Now let us now quickly look at some vital terminology that we're going to be using in our calculation. So the conditions that, if you see this condition, you are going to know if it is a constant volume or a constant temperature, is that again, or it is a constant pressure and the likes. Okay, let us consider this diagram. Let's consider this diagram. So I'm considering a diagram now. Okay, let me draw a curve. Do I have curve here? Curve. No. Okay. Use my pen. Ordinarily, let me check this and use my pen. Okay. So let me have a constant. Beautiful. Okay, so in this case now we have our PV diagram. P is pressure, then our V is what? The volume. 1, 2, so 2, 2. And this is 2. this is a process. This is a process like this. You're moving from one place to another is a process. So this one is 1, this is 1. This is a process. Is that taken? Now let us now see all these processes now. Number 1. Okay, we can also have, because you can see with that we have entropy here. TS diagram. If you are considering an entropy, that's a TS diagram. Okay, let me call this, this is temperature and this is entropy. We call this one 0.1, 2, 3 and 4. Is that taken? Okay, so let us consider them one after the other. So we have adiabatic process or adiabatic system. So an adiabatic system is a system in which it is thermally insulated, meaning that your Q is equals to 0. When we say that what something is thermally insulated, it simply means that what Q, the heat, there is no heat. We've considered isolated system. An isolated system is an adiabatic system, meaning that there is no what? There is no heat. Is that taken? For an isolated system, the number 1 is that mass are not being transferred, 1, and secondly, the heat and the work, there is no heat and there is no work. You understand now? Across the boundary. So that's an isolated what? System. Now, an adiabatic is now an isolated system because your Q is equals to what? Is equals to 0. Is that taken? So here we now have the general formula for an adiabatic process is PV gamma is equals to C. We are still going to use it. We're still coming back to that formula as time goes on. So here, what is now the diagram of an adiabatic process? This is the diagram. This curve is an adiabatic process. It goes like this. This is an adiabatic process. Is that taken? An adiabatic process is, so an adiabatic process is an insulated, thermally insulated. It is thermally insulated. Is that taken? So that's just it. Now another one, I've shown you the diagram of an adiabatic process. So okay, we have isothermal. Isothermal. When we say a process is isothermal, is that taken? It simply means that the temperature of the system is constant. Isothermal. 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 The temperature is what? Is constant. The temperature is constant. The temperature is constant. You can see now, look at this diagram now. This is TS diagram. So at this point we have T. Is that taken? So your T3, your T2 is equals to your T3. Is that taken? This is what an isothermal process or system. This is an isothermal what? So that it occurs at a constant temperature. The temperature did not change. Is that taken? This is an isothermal temperature. It simply means that temperature it occurs at constant temperature. Another one is now what? Isobaric. Isobaric. Here baric, that's pressure. Isobaric. And isobaric, it simply means that what? Pressure occurs at constant, the heat occurs at constant pressure. Look at it. This is PV diagram. For PV diagram, I'm going to get that one. So this is 1 to 2. So it is an isobaric process. This one is an isobaric what? Process. Okay. For better understanding, let me call this one AB. So line AB is an isobaric process. So A to B is an isobaric what? Process. Process at constant pressure. This one is at constant temperature. You get that on TS diagram. Is that taken? So the next one we have is now what? Isochoric. 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 Isochoric is it simply means that heat occurs at constant volume. So which line is that one? So it is this one. This is the volume axis, the abscissa. So this one is now, it goes up at constant volume. The volume did not change, but it is what occurs at that particular what state. I can call this one, let me call it CD. So isochloric. C to D is what? Isochloric at constant volume. Please don't forget, at constant volume is isochloric. So isentropic. So an isentropic, it means that what? Entropy is constant. Isentropy, that's what? Entropy is what? Is constant. Where is entropy constant here? Let us consider this what? TS diagram. If you are hearing entropy, so it simply means that what? You need TS diagram. So don't mind my drawing, sorry. So here you can see that what? The entropy S1, and this one is what? S4. Is that again? Your S1 is equals to your S2, and your S4 is equals to your S3. Is that again? This is an isentropic. So it's an isentropic process. So isentropic process. Here S1 is equals to, the diagram I consider is equals to S2. Yes, S1 is equals to S2. S1 is equals to S2 at constant what? Entropy. At constant entropy. And finally we have isentalpic. So for an isentalpic, it simply means that it occurs at constant enthalpy. And what's the symbol of enthalpy? That's H. So when you have what? Your H1 is equals to H2. That's what? At constant enthalpy. So these are the things that what you must understand. So we have isothermal, that's at constant temperature. Isobaric at constant pressure. Isochloric is what? At constant volume. Isentropic at constant entropy. Then isenthalpic, it is at constant enthalpy. So we have what we call thermal efficiency. This is thermal efficiency. This is symbol thermal. You know, when you are doing machines, you say that input minus output, over what? Over input. What's our input? Is that your input is Q. You apply Q1, then your output is what? Is Q2 over Q1. So if I divide this, if I split this, that's Q1 over Q1 minus Q2 over Q1. Then I'm going to have my this for thermal is equals to 1 minus Q2 over Q1. We're still coming back to go further in what? In this, where your Q1 is heat received. So since the system has received heat, it's going to reject some quantity of heat as well in form of work. So this one is what? Heat rejected. We just started. So we stop here, then we'll continue in our next class. Thank you.